where planets form. As this classic plot from Obergedal 2011, getting both the oxygen and carbon is crucial for us to understand where in the protoplanetary disk planets form and how they form. So without further ado, we have a great idea. Let's go measure some carbon and oxygen ratios on hot Jupiters. And we know just the right instrument, SPIRou on CFHD on Mauna Kea. So what do you have for observations? We actually observed Tau Booby for 5 nights total, spanning a total of 20 hours. We observed in thermal emission, so the planet's day side. So here's a schematic of the observations where we always look close to where the planet would eclipse. Now recall that Tau Boötis b is actually a non-transiting exoplanet. So we don't see a transit from our point of view. So we're just looking at the thermal emission, no eclipse. And again, we use the SPIRou spectrograph. So a slight reminder of the specs. This covers the full 1 to 2.5 microns at a resolution of 70,000. And yeah, thermal emission, lots of hours. So after observing, we get a bunch of data. Now, as we've seen throughout the week, it's crucial, especially in the near infrared, that before we go on to do any analysis with the planet signature, we first have to get rid of or remove anything from the star or from tellurics. We have these pesky tellurics ruining all our hopes and dreams about finding planet signals. We have to clean them up. So here's a schematic of the raw data as it comes in, and we have to do some sort of alignment, and then we run it through the machinery, in this case, like fitting and principal component analysis, to basically get rid of all contributions from the star and the Earth. And on the bottom panel here, what looks really just like noise, we hope that the planet signal is actually buried in there in that noise, and we can hopefully recover it with a cross correlation. Okay, so now that we have reduced data, rid of all the unwanted contaminations, we can go and search for a water signal. Now we expect water is a very favorable target. SPIRou is a very good instrument for this. We should be able to find water no problem. But first we have to make sure we have models. So models representing the planet's atmosphere. So we used the Scarlet atmospheric modeling framework, and we generated thermal emission models of Tau Booby's atmosphere. And as you can see here in the upper panel, we made separate models for different molecular species, in this case, carbon monoxide and water. And so we can use these templates to cross-correlate and see if we can find any of these species in Tau Boo's atmosphere. Okay, on to the results. Wait a minute, what's this? We actually expected to find a super strong water detection, but alas, when we look at where the planet is expected to be in this KP and VSIS plot, we don't actually find anything when we cross-correlate with a water template. What's going on here? So I just want to stress that this was totally unexpected for us. We actually spent many months trying to refine our reduction just to make sure that we weren't doing something wrong. And after a while, almost having given up, we're like, well, what do we have to lose? We might as well look for CO anyways. And actually, when we did look for CO, to our surprise, we expected CO would be much harder to find there in water. We did find CO exactly matching the expected location from previous literature results. So again, stressing that this is totally not expected. We find CO, but no water, CO and absorption, very odd. But moving on, what can we learn from this? In these maps, typically we have a detection, but we can go more than just finding a detection. By the shape of the lines in the model we use, we can actually retrieve what an average CO line shape would look like in Tau Booby's atmosphere. And from the precise shape of the lines, we can actually retrieve the temperature structure shown here on the right. So we were able to retrieve this non-inverted temperature structure of Tau Booby's atmosphere. But why stop at just water and CO? There are more molecules. And if we really want to get the carbon and oxygen budgets right, we have to make sure that we encompass all of the major carbon and oxygen bearing molecules. And so we decided to investigate all of these molecules shown here that have significant opacity in the bandpass of SPIRou shown here between 1 and 2.5 microns. So we included these 8 molecules and did a full retrieval using the same technique presented earlier today by Matteo, the CCF to log likelihood mapping. And without further ado, this is the full retrieval results that we get. Sorry for the many panels, but here we have again the retrieved temperature structure we got. And this massive corner plot, we just have basically the separate abundance of different species. So water, CO, methane, etc. And we also simultaneously retrieved a gray cloud deck, as well as other orbital parameters. Now, really the takeaway messages from all of this is, again, the temperature structure is non-inverted. We were able to very tightly constrain the CO abundance, shown in this panel here, to be roughly 5 times higher than solar. So a super solar CO abundance. For the water, however, we only got like a very tight upper limit, so that we find a very depleted water abundance. And the other molecules that we looked for, we only found upper limits for those as well. And we find a relatively cloud-free atmosphere with, we don't expect significant clouds higher than the 0.26 pressure level. Okay, so we have all of these molecular volume mixing ratios. What can we do from here? We can actually basically just count them, and we can infer elemental abundance ratios. So here we have the C/H ratio. We basically count all of the carbons that are in our atmosphere. And shown here, we have the probability density of the C/H ratio on Tau Boo, shown in red, compared to the C/H ratio precisely measured from Jupiter. And both of these are supersolar, shown here in red. So we actually find that the C/H ratio that we infer for Tau Boo, larger error bars, but it actually closely matches the value for Jupiter. So that's pretty cool, I would say. Now moving on, we can do the same thing for the oxygen budget. So we measure the O2H ratio. And again, shown here, we have the O2H ratio plotted relative to the value for Jupiter. Now, in this case, the value for Jupiter has much wider error bars because, as I mentioned previously, measuring oxygen on Jupiter, because it's such a cold planet, is very difficult, so larger error bars. But even with this, we see that our values are more or less consistent. And you might notice that we have a shaded area over here because oxygen is a bit trickier than carbon, because oxygen has a tendency to condense out of the atmosphere. So when we're observing, we're probing the gas phase. We're not probing species that might be condensed out into clouds. So if we're counting oxygen and carbon abundances, we might be missing species that are condensed out. And so anything that form clouds, such as MgSiO3, they take out oxygen from the atmosphere. But they can only take out so much from the gas phase, and we can actually infer the maximum amount they can take out. And so it adds kind of a uncertainty over here. We can see this more when we combine the C/H ratio and the O2H ratio to get the C/O ratio, which is all the buzz for planet formation. So over here, we see the C/O ratio. And in white is what we infer from the gas phase. You see a very, very tight peak around close to 1. Now, what does this mean? This means we basically only find CO. C has one O, CO has one C and one O. So C/O of 1. But again, we might be missing a lot of O. So depending on the species shown over here that tend to condense out into gas phase, if we have aluminum species condensing into clouds or iron or silicates, these can all take out of the oxygen in the atmosphere. And so our C/O ratio could technically be anything up to 0.6. But even if we remove all the oxygen we cannot go lower than 0.6. So really our claim is that the C/O ratio on tau B is somewhere between 0.6 and 1 is what we think. Now, how does tau fare versus, let's say, other planets? So here I'm comparing what we see for tau B with kind of the two probably most well-characterized exoplanets, the trademarks HD189 and HD209. And over here, I'm plotting the water abundance and the CO abundance. And in colors, at the top, the dark color is supersolar and the light color is subsolar. So at the top panel over here, you can see the water abundances inferred for HD189, HD209, and tau. Notice that all three of them are subsolar. Now, if we look at the bottom panel, we see the same thing, but for CO abundance. Now notice that all three of them are supersolar. So obviously we'll need a lot more data points, but this seems to already point towards a trend that we have subsolar water abundances and supersolar CO abundances. And together, this most likely means that these planets have a not a low metallicity, but rather an elevated C/O ratio. So again, supersolar metallicity and supersolar C/O ratio. Now it's the combination of these that is actually quite interesting from a planet formation perspective, because there's only so many ways that you can make a planet that is supersolar in metallicity and still maintain a high C/O ratio. And most likely this would mean that the planets, hot Jupiters like tau B, formed much further out in the disk and later migrated to become hot Jupiters. In summary, we observed tau B with SPIRou. We found a CO abundance that is supersolar, and we found a depletion of water. And this depletion is not due to a low metallicity, but rather a supersolar C/O ratio. So all the oxygen is held in CO. And the favored mechanism for this is most likely gas secretion beyond the water ice line, followed by migration disk-free with limited pebble accretion. Thank you very much, and I'll take any questions.
Thanks very much, Stefan. So please do raise your hand, anyone, if you have any questions. Okay, we have a question from Jens. Take it away.
Hi, Stefan. Very, very good stuff. I know we've talked about this before, of course. I was just wondering, if you go back to your retrieval, did you include clouds? And is it right? You do, right? You have is that a lower limit or an upper limit to the cloud top pressure? Anyway, my question is it plausible? I think if I remember correctly, that these these water lines are, like, in absolute sense, typically a bit less deep than the CO lines. Correct me if I'm wrong about that. Is it at all plausible that you might be losing some of or all of your water lines in a cloud deck, and that you're essentially hiding H2O that you think isn't there, but actually is hidden just because there is a cloud, or maybe one of these condensates that you mentioned sort of blocking that?
And that's an interesting point. So first of all, yeah, we included clouds, but only kind of a gray cloud deck. And yeah, we find a, I guess depending on how you think in altitude or pressure, but the clouds could only be as high as 0.26 bar, which is still fairly relatively deep in the atmosphere. And so we would still expect water to be above that pressure layer. Now, if somehow the water abundance is skewed so that it's contained mostly beneath the cloud deck, then yeah, we would not be sensitive to that. And we could, in that sense, the water could be hidden from us. So yeah, I guess that's a possibility, but there's probably no way for us to find out.
So it's a bit of a chemistry argument saying that if your cloud is there that deep, then you would not expect to deplete it all the way above that. So why would you hide it? Yeah, I see. Super interesting work. Thank you.
If I may, I have one quick question while we're on this slide. So I see that you also have a PT profile that, if I recall from your paper, has lots of different free parameters at every single pressure level. So you've got a lot of free parameters in addition to the ones we see on the corner plot here. So could you give us an idea of how long this retrieval took to run and whether you had to do it on a cluster? And yeah, so what were the computational requirements?
Yeah, so good point. So as also Matteo and others have mentioned, these high resolution retrievals are very computationally expensive. So we have 8 molecular abundances, a few other parameters. And in our TP profile, we actually have 15 separate points connected with a smoothing factor. I think we have a total of 27 parameters in the retrieval. And the retrievals has to compute models at high resolution. So yeah, very long. We do have to run these on clusters. We do have to use parallelization. And even then, we're talking on the month scale. So like maybe 2 months. So yeah, long time to twirl your thumbs to wait.
Well, thank you very much. And well, I think we'll move on to our next talk then. So Eva, would you be able to share your screen? Okay, so
see my screen.
Yep, that looks fantastic. So yeah, so we're going to hear from Eva-Maria Ahrer, apologies if I mispronounce your name, from the University of Warwick now. Now we're going to be switching down to, I presume, low resolution transmission spectroscopy. So yeah, tell us about WASP-94AB, please.
Yeah, hello everyone. Thank you for the nice introduction, Ryan, and thanks everyone for allowing me to speak today to you. So you were close enough. So my name is Eva-Maria Ahrer, German, but most people just call me Evie, so please go ahead, do that, it's easier. And yeah, today I'd like to talk to you about, well, large beasts and WASP-94AB and what we found. And indeed, it is low resolution. So we have heard about a lot of high resolution, and this is like a bit different and very different in terms of data reduction as well. And I just want to highlight quickly supervisor Pete Wheatley, nothing happens without him, and my collaborators James, Sid, George, and Tom. Okay, first I'd like to just quickly give an overview about large beasts. So one of my favorite acronyms really, and it stands for low resolution ground-based exoplanet atmospheres. So we're using transmission spectroscopy very long, but in the end, its aim is just to provide a large sample of optical transmission spectroscopy. So we have a lot of had a lot of infrared talks today as well. So we're here in the optical low resolution. And using 4-meter class telescopes, so not VLT or anything, but instead we have used the William Herschel telescope, and today I'm going to talk about the new technology telescope. And on the right here, you can already see like the published results, a lot from James as well, as he started large beasts. And you can see a lot of like clouds, hazes, and also some detection of sodium and potassium in there. And yeah, if you're interested, there's also a website with large beasts with all the with the figure and all of the results. Okay, but my system today that I want to talk about is WASP-94, which is really, really interesting, as it has two, like a binary star system, and it has nimbus A and B, basically similar spectral type and very similar magnitude. They also both have a hot Jupiter orbiting. So I'll talk about AB, which is like half the mass of Jupiter, but has like an inflated radius, so 1.7 radius of Jupiter. And then there's WASP-94b, who has only been detected in the radial velocity so far. So it's non-transiting. And it's quite interesting to have like a system like this, to have both orbiting and one transiting and the other one doesn't. And in addition to this, WASP-94b has also shown to be misaligned and likely in a retrograde orbit. And with its equilibrium temperature, and it's like very close to the star, low mass, inflated radius, it's shown to have a very high atmospheric scale height, so great for transmission spectroscopy. So if I quickly go through observations, so what we did, or like we had this one transit with NTT and EFOSC in August 17, and we do long slit spectroscopy, meaning for those of you who don't know what this exactly is in low resolution, you place two stars, so in this sense a comparison star and target star, along a slit, and then you put a grism. So here in the middle, you can kind of see that they're like a raw science frame. It's kind of cropped off at the side because they're close together anyway, the stars. And basically the y direction would then be the wavelength. So this is great because those two stars, WASP-94a and B, are close enough together that you can use them as the binary companion as a comparison star, but they're not that close that they bleed into each other. So if you see here on the right, there's the two spectrums of the comparison star and target star in red and blue, and they basically show the exact same like spectra. So that's great for getting rid of any like atmospheric effects from the Earth. I've also highlighted here like sodium in green. So around sodium, we choose to have smaller bins so that to pick out the sodium signal better. Overall, the bins are generally around 200 angstrom wide. And overall, we cover, as you can see, like around 3,900 to 7,100 angstroms. Okay. So what did we get in the end? So this is our white light curve. So you see two figures here. So on the left, we've just used polynomial detrending. On the right, we've used GP detrending. This was just to make sure that our like transmission spectrum is not like dependent on any detrending method. So on the left, we just use a second order polynomial. On the right, then we use GPs. Of course, GPs are known to be like better or like in capturing systematics. So this is what we did to go forward and do our atmospheric retrieval with. And here we use two kernels. So one on like sky background, and both kernels are exponential square for those of you who also use GPs and would like to know that. And so we have the sky background in orange, and then in blue that would be the derotator, which is kind of similar to like the shift along in the slit over the night, which pretty nicely captures then our systematics. Then here, just quickly, for those of you interested, how all the spectroscopic light curves look like and the fitting. But interestingly, we were thinking about how we could decrease the uncertainty on our transmission spectrum. Because if you use GPs, your errors might be inflated or get inflated. And our transmission spectrum looked like the scattering into the transmission spectrum was higher, was like lower than the actual uncertainty. So it looked like there was some factor uncertainties, like some systematic going on that we don't account for. And we were thinking about that this could be solved kind of by, instead of fitting all the spectroscopic light curves individually, we fit them all together at the same time. And the GP has like some shared hyperparameters, in that case, the length scales, so how correlated the points are next to each other. And but still having individually fit amplitudes and also individually fitted white noise kernel. So we kind of try to decrease the like freedom that the GP has without taking away, like kind of like a common noise mode without restricting it too much, if that makes sense, hopefully. And we were able to decrease the precision in the transmission spectrum by like 50, 60 ppm. So in the end, we had an average of 128 parts per million across the 200 angstrom bins. So this is what the transmission spectrum looked like. There's still some, like, we still think that there's some, like the errors are slightly inflated, as they still kind of like the scatter is still lower than actual the error bars. But I include also for just to show the two different detrending methods again, and that they basically show the same shape, just with different sized error bars. And you can see here quite nicely the sodium signal at well, around 5,900 angstrom. You can also see that the scattering slope towards the blue, which I'll come back to later. But first, let's look at the sodium signal, because the first thing that came to us, or like came to mind when we looked at this, was that it looks slightly broadened, like that it just kind of looks a bit broad. I skipped over that now. So what is it broad? So to investigate this further, we looked at the transmission spectrum, but at the best resolution that our telescope could get, so at Nyquist sampling, which of course resulted in very high error bars. And we tried to fit just a Gaussian with the resolution of the telescope at 27 angstrom, and also fitting a Voigt profile. So a Voigt profile is just a convolution then of the instrumental Gaussian and the pressure proton sodium Lorentzian profile. So this is what you can see in the orange and then the blue. So you have the Gaussian profile and the blue, the Voigt profile. While we do think that it kind of looks like the blue one fits better, it's really hard to say with like the really high scatter. And also the Bayesian evidence favors the instrumental resolution. So just having a Gaussian and no broadening happening. For reference, the best broad fit was 78 angstrom, so well, quite a lot broader than actual the instrumental like broadening. But this is definitely something that should be investigated with higher resolution with better uncertainties. So we shall see on that. Then looking at the scattering slope, and we've done some retrievals. So we've looked with Blayton, we used like two different models. One of them where the model is fixed to Rayleigh scattering, so where the scattering gradient is fixed to 4, and that is the green one in here. And then just letting it just free choose, and that's done at a 13.6, which is fairly high and fairly high uncertainty as well. But just not consistent with 4, and it does look like it fits better. And the Bayesian evidence slightly favors the free scattering gradient, but with the errors kind of like it's just a slightly favor, so not like just around 1 sigma. So we wouldn't say that this is just like tentative evidence. And if you use the polynomial detrending, so this is all the GP one, then the favoring of the free scattering gradient would be higher. But that's something we just need more data to put this further. So this is kind of the question, like what could cause this kind of enhanced Rayleigh scattering? There are of course a lot of theories, but you might ask now, what about stellar activity? Stellar activity can also cause a scattering slope to appear. And so we've been looking at WASP-94A, and since it is a late F-type star, and it was predicted to have 2.7 to 7% of like a spot and Beckley covering fraction, we don't think that it is that there's stellar activity playing part in this transmission spectrum. And it's also haven't shown up any variation in the photometry in the when it was discovered in 2014. But nevertheless, we did a Platon retrieval where we looked at put this like limit on the covering fraction in, and it didn't account, or like it wasn't able to account for all of the scattering slope that we've seen. So we were thinking about if there's stellar activity, we might as well look into the log R prime HK factor of WASP-94A. So we gone into ESO archive and got out some HARPS data, and we found that this is the H and K lines. And for those of you not aware, there's the log R prime HK is basically a stellar activity indicator. It's kind of like an index in where you used to like the flux ratios between H and K and some correction factors. But you can see in the middle, there's basically like if it would be active, you would have emission there, which we can't see. And the log R prime HK is at -5.2. And if you look at the literature, basically no activity would mean -5.1 for FG and K stars. So this is actually below the like basal limit as it's called. And if you actually zoom in on those, you kind of see that it kind of looks a little bit like there's absorption there. And it has been suggested before that there might be some like planetary material removed and would kind of like cause an absorption in the H and K lines and then go below this basal limit and actually absorbing the stellar emission. So in the end, from log R prime HK, we can't actually say if the star is active or not, because it might as well be absorbed by this planetary material. So we don't, like in the end, we think there's no, like we can't rule out stellar activity having any effect, but we don't think so. Like doesn't seem to be very likely. So the conclusions of my work basically are, so this is the first transmission spectrum, or like long slit transmission spectroscopy done with NTT EFOSC2. And it's also the first transmission spectrum to date from WASP-94AB. So please follow up this amazing planet. I hope I convinced you that it's very interesting. And we, just because of our like perfect conditions and the simultaneous fitting, and with the really great, like its companion star being a very great comparison star, we had a really good precision to this like average. We also managed to detect, well, you've seen the sodium feature, and which is potentially broad, but we cannot say that for sure. And we found the scattering slope with some evidence for enhanced slope. And we've been looking at the calcium H and K lines, which suggest an absorption. And yeah, I just hope that I've all convinced you to do follow-up observations, and I'll hear a lot about this planet soon. So thanks for your attention, and take any questions.
Okay, please raise your hand if you have any questions, anyone. While we wait for people to come up with their creative questions, I will take the liberty to ask one then. So I was curious, what is the Bayesian evidence for the detection of sodium, and were the Platon retrievals able to tell you anything about the abundance of sodium?
The detection itself of sodium is like at 4.9 sigma.
Oh, that's fantastic.
Yeah, so that's really great. And the abundance, like in Platon, it's kind of the abundance goes all together like metallicity, and so I can't really say anything about the abundance. Something we should definitely look into, but I have the feeling we probably can't say much because it's like lowest resolution.
Okay. I see we have a question from Elia. Take it away.
Hi. First of all, excellent work. Yeah, as I said in the chat, getting results from one of the granddads at ESO. It's a very old instrument. So my question was, do you know if there are V sin I measurements from high resolution spectra of the two components?
From WASP-94A, yes, there's a V sin I measurements, but I don't know on top of my head. Or I can. It's from the discovery paper, so from Nevoy et al. So that one, yeah.
The reason I ask is if they in fact have similar V sin I measurements, that means that probably the spin axes are more or less aligned. And if we assume that the other planets in 94b to be roughly kind of coplanar, then that's obviously it's not transiting, but it's probably close to transit. So that might even be a good target also for doing reflection spectroscopy in high resolution, and then could really do a kind of a, because you have it in really nice laboratory, right, to do comparative analysis. So that would be nice to look into.
Yeah, you definitely should. I don't remember if it was 94B as a VSON measurement, but 94A for sure. But I'm not sure if they managed for 94B.
Okay, you can check.
Yeah, definitely
Great,
follow up this.
That's all. Feel free to ask your question.
Hi, Eva. That's a very nice talk. Thank you. One question I was just thinking, one of the other ground-based sodium detections we have is, I think, WASP-96 from VLT. And curiously, that's also a binary system where you have a really good comparison star right next to it. So I'm wondering if this is a pattern, or if that's like one of the best systems that we can actually get these detections.
Yeah, I do think so, because it is one of the best like positions what we had from large beasts so far, so from all of the William Herschel as well. So I do think it helps a lot with the position if you have a binary system. So or maybe that's where we should be going, and just look at all the binary systems and have a good comparison star. It did help a lot.
Thank you.
Okay, so if we don't have any more questions, I think we will actually go to our tea break 1 minute early. Well done on keeping to time, everyone. And so we will be back in 21 minutes to hear an invited talk about some multidimensional effects from exoplanet transits. It's going to be a lot of fun. So see you in 21 minutes, everyone.